Did you know that flipping the bits of a number, literally reversing them, is a favorite falling interview question? Reverse bits is a classic pattern mastery 100 problem that seems simple, but it reveals who really understands how data is stored and manipulated at the lowest level. Master this, and you'll unlock a new level of confidence for bitwise questions, data encoding, and optimization. Let's break it down. Given a 32-bit unsigned integer, reverse its bits and return the resulting integer. For example, if the input is 100 in binary, you need to flip the bit so it becomes 001. Let's assess our approach. The brute force way is actually perfect here. Loop through all 32 bits, and for each one, shift the answer left, add the current bit from n, and shift n right to process the next bit. This runs in 01 time, since 32 is constant, and 01 space. Here's the structure. Initialize result to 0 for 32 times, or as many as the number's bit length. Shift result left by 1 to make space for the next bit. Add the least significant bit of n to result or equals n and 1. Shift n right by 1 to process the next bit. When done, return result. Let's try to implement it using solution 1. We begin by creating a class called solution, just a clean container to hold our method. Think of it as a folder that keeps our function neatly organized. Inside the class, we define a function named reverseBits. This function takes a 32-bit unsigned integer n and flips the order of its bits. So the very last bit becomes the first, the second last becomes the second, and so on. Like reversing a line of dominoes. We start by creating a variable called result, set to 0. This will slowly build up the reversed number bit by bit. Imagine an empty bucket that we'll keep dropping bits into. Now we loop exactly 32 times, once for each bit in a 32-bit integer. This means the runtime is 01 because we always do a fixed number of operations, regardless of input size. This is the heart of the algorithm. Let's break it down. n and 1 extracts the least significant bit, the rightmost bit, of n. Result 1 shifts our current result left by 1 spot, making room for the new bit. Then we OR them together. This appends the bit from n to the end of result. It's like sliding your result over by 1 space and sticking the new bit onto the end. Here we write shift n by 1 bit. This removes the bit we just used and moves the next bit into position. Think of it like trimming off the bit we already processed and pulling the next one forward. After processing all 32 bits, our result now contains the fully reversed bit pattern. We simply return it. Clean, simple, and ready to use. Solution 1 test case explanation. Reverse bits. 32-bit binary reversal case 1, n equals 43,261,596. Let's test our function using this input, 43,261,596. This number represents a 32-bit unsigned integer, and our goal is to reverse all 32 bits of its binary form. Here's why the solution works. The algorithm builds the reversed number 1 bit at a time. We look at the least significant bit of n, shift our result left, and append that bit to the end. We repeat this for all 32 bits, slowly flipping the binary sequence from back to front. For the input 43,261,596, its 32-bit binary form reversed becomes the number 964,176,192. And that's exactly what our program outputs, 964,176,192. Perfect match with the expected result. So, our implementation is correct. The algorithm successfully reverses all 32 bits of the input integer using clean bit shifting and reconstruction, efficient, accurate, and reliable across all test cases. Solution 2. Now we're walking through solution 2, which uses string manipulation instead of bit operations. We begin by defining a class called solution. Just like before, this class is simply a container that organizes our function neatly, like placing it in its own folder. Inside the class, we define a method named reverseBits. This method takes a number n, and our mission is to reverse its 32-bit binary representation. Instead of doing this bit by bit, we're going to take a more human-friendly approach using strings. This line converts the number n into a binary string. Bit n gives us something like 0b1011. 2 removes the 0b prefix, leaving just the bits. sfill32 pads the string with leading zeros so it becomes exactly 32 bits long, because missing zeros in front would mess up the reversal. It's like writing the number neatly on a 32 square grid. Pause. Converting and padding the string is 01 since the length is fixed at 32. Here we reverse the entire binary string using Python's slicing trick, -1. This flips the order of the bits so the last becomes the first, just like flipping a row of domino tiles. This reversal is also 01 because the string is always exactly 32 characters. Finally, we convert the reversed binary string back into an integer using int2, which interprets the string as base 2. This gives us the correct reversed bits number as a normal integer, and that's our result, clean and readable. And that's how this algorithm works. It first turns the number into a padded 32-bit string, then reverses the string and converts it back into an integer. Efficient, simple, and elegant. Solution 2. Test case explanation, reverse bits, string method. Case 2. Now let's try the input, 2,147,483,644. Again, we convert it to a 32-bit binary string and flip every bit's position from start to end. The reverse string corresponds to the value 1,073,741,822 when converted back to an integer. And the program outputs 1,073,741,822, exactly the expected result. So, our implementation is correct. The algorithm successfully reverses all 32 bits by using a clean binary string transformation. Simple, accurate, and reliable across all test cases. Alright, let's quickly recap what we learned about reversing bits in a 32-bit unsigned integer. Breakdown recap. We started by understanding that the task is to flip the order of bits, turning the least significant bit into the most significant, and vice versa. Conceptually, it's like mirroring the binary pattern of the number. Assess recap. We realized that a simple loop-based approach works best here. There's no need for optimization tricks. Iterating through all 32 bits is already efficient since the bit count never changes. Structure recap. We built our logic step by step. Initialize a result, shift it left each time to make space, take the current bit from the original number, and move to the next bit by shifting right. Implement recap. We then implemented this logic directly in LeetCode, and the code ran smoothly without any syntax or logical issues. Check recap. Finally, we verified our result using LeetCode's test cases, confirming that our function correctly reversed the bits every single time. The key takeaway here is that sometimes the most direct approach, like looping through each bit, can be both clean and optimal. Bit manipulation problems often reward clarity over complexity.